Welcome to some more MRI physics from MRInotes.com. The topic here is bandwidth. Bandwidth is a parameter that the user can vary, and it has some important effects on the image. So here we're going to look at what is bandwidth, what are these effects, and how can you use bandwidth to your advantage in imaging. Okay, so what does bandwidth mean? Well, bandwidth is just a general term for the range of frequencies in a signal. It's not an MRI specific term. For example, say all the information in some signal is contained within 2 kHz and 5 kHz. In other words, there's nothing useful in that signal below 2 kHz or above 5 kHz. Then we would say the bandwidth of that signal is 3 kHz. When it comes to MRI, we have two types of bandwidth. We have the bandwidth associated with the transmitter, so the bandwidth of, say, a 90-degree pulse or a 180-degree pulse. And then we have the bandwidth of the receiver. So the bandwidth of the receiver is the bandwidth, the range of frequencies that the machine will listen for. The receiver bandwidth is also called water-fat shift on some systems. The transmitter bandwidth, you don't have any direct control on this. You may have come across it before where slice thickness came up and how slice thickness is set in MR. The transmitter bandwidth is instrumental in how the machine sets up a particular slice thickness, but you don't have any direct control. You can't sit down and specify the transmitter bandwidth. The receiver bandwidth, on the other hand, you do have direct control, so you can sit at the console and type in a figure for the bandwidth that you want. And it has an impact on the image. It's the receiver bandwidth that this talk is about exclusively, and in general, when you hear bandwidth in MR, we're talking about receiver bandwidth, not transmitter bandwidth, except in the very specific case of slice selection. Okay, so something that bandwidth has a major influence on is called chemical shift artifact. Now, you may have seen this before. It's where an image has this kind of appearance. So what we get with this artifact is on one side of a boundary or an organ, we can see a bright or hyperintense line. And then if you move to the other side of the organ, you can see a dark or hypointense boundary. And you can see it's very pronounced in this image. Everything has a very clear delineation, very clear boundary because of this, this artifact. And what we'll see, of course, is that this chemical shift artifact is dependent on the bandwidth. So by controlling the bandwidth setting, you can determine whether this is a strong effect or a weak effect. Okay, so to look a little more at what this chemical shift artifact is. So to understand chemical shift artifact, you need to think of the MR image as being made up of two underlying images, a water image and a fat image. So if you think about the signal in MR, a lot of it is coming from water and some of it is coming from fat. And each of those can be thought of as making up their own image. Now, normally they are sitting on top of one another or appear to be fully sitting on top of one another. But with chemical shift artifact, what happens is there is slippage between those two images in one direction. Okay? So it looks like our water image is pulled one way and our fat image is pulled one way. And that gives rise to these boundaries that we see in chemical shift. And if you notice the slippage, it's along one direction. And that direction is always going to be the direction of the frequency encode gradient. and we'll see why shortly. Okay, so what is this bandwidth thing? What's causing it, or what's making it? Well, it's actually one of the gradients that is responsible for the bandwidth. Here I've got a spin echo timing diagram, so the usual thing, radio frequency transmitter, and three gradient directions: slice direction, phase encoding direction, and frequency encoding direction. And then, of course, we have the signal, what's picked up by the radio frequency coil, and our echo here. Now, it's the frequency encoding gradient that is going to be the source, or the reason for, or what controls our bandwidth. Okay, so let's review what this gradient is doing, the frequency encode gradient. So let's imagine we are imaging some object and we have a cross-section here through it, this thing in blue, and we are taking a slice. It has a frequency encode direction, it has a phase encode direction as per normal. When we switch on that frequency encode gradient, what are we doing? What we're doing is we're introducing a variation in the magnetic field strength in the direction of the frequency encode gradient. So here we're showing field strength on this axis, and we're seeing how that varies as you move left and right. So a location here in the object will have a higher field strength than a location here in the middle, or a location here on the left. And of course the field strength in the middle, or along the line through isocenter, it won't be zero, it'll be whatever that MR system's field strength is. So if it's a 1.5T system, it's 1.5T here in the middle, and 3T system is 3T in the middle, and all the variation is happening above and below that figure. So remember what the variation in magnetic field strength will do. Just through the simple Larmor equation, variation in field strength means variation in Larmor frequency. So when we think of all the spins that are precessing throughout this volume, the spins that are experiencing the higher field strengths are going to spin faster than the ones experiencing the lower field strengths. So if we think about moving from one edge of that object to the other, there is going to be a variation in precessional frequency. So we've shown here that this edge is precessing 8 kHz slower than the center, and this edge is precessing 8 kHz higher than center. So as you move from left to right, the precessional frequency changes by a total of 16 kHz. So really that means is that the signal that we are going to pick up is going to have a range of plus or minus 8 kHz around whatever the Larmor frequency at isocenter is. In other words, it's going to have a bandwidth of 16 kHz. Okay, now there's nothing special about a bandwidth of 16 kHz, just using that here as a illustration. But do notice that it's the gradient field strength, it's the steepness of this line of the gradient, frequency encode gradient, that is going to determine that bandwidth. Because, for example, if we went for a steeper gradient, say twice as steep as this gradient, we get the same effect, but now we get a bigger difference in precessional frequencies as we move from one edge to the other, simply because we have a bigger field strength difference as we move from one edge to the other. So that means we have twice the bandwidth in this case that we do in the previous case. So that's 32 kHz full bandwidth versus 16 kHz on the left. So the bandwidth we set ultimately will determine the bandwidth of the echoes that are picked up and written to K-space. I've shown the two examples here again, the 16 kilohertz and 32 kilohertz full bandwidth, this time with the resulting echoes indicated. Now, the general shape of the echoes is no surprise. They just wax and wane the way echoes do. But notice that the case where we have double the bandwidth, the echo has half the duration. So, slightly confusingly, a broad bandwidth is associated with a narrow echo, or narrow in time, and vice versa. So why is this? Okay, well, first of all, remember that during echo formation, the frequency encode gradient will be switched on. So the conditions shown here hold. In other words, there will be a difference in Larmor frequency moving from one side to another in the frequency encoding direction. And the echo, of course, in each case is just made up of the summation of signal that's evolving from this excited volume. So depending on the location, the volume is contributing a different frequency to the signal, and overall, as it's all added up, it forms this shape. Now, the only difference really between the broadband case and the narrowband case is that in the broad bandwidth case, things are happening twice as quickly as they are in the narrow bandwidth case shown here. So really, all that means is we're going to get the same shape, we're going to get an echo, but it evolves twice as quickly. So that's just going to mean that the echo for the broad bandwidth example given will be half the duration of the echo for the narrow bandwidth example given. Okay, so let's look at the frequency encoding gradient here again, and how the bandwidth setting influences that. So just zooming up on this part, the readout or frequency encode gradient, which again is on as the echo is forming. So we could have a narrow bandwidth case. What does narrow bandwidth means? It means the echo is going to be quite long. So it means that the gradient is going to be switched on for a relatively long duration. Now, if you recall, what's important about a gradient is the total area under the curve. So if a gradient is doing a particular job, which in this case is frequency encoding, we're going to have to achieve a certain area underneath this curve. So a certain duration multiplied by amplitude to give us a certain area. Now we could deliver that area in a different way. We could deliver it like this, in which case we have the same area under the gradient curves, except this time we have a shorter duration. What does that mean? That means we are going to have stronger gradient on for a shorter period, which means that our echo is going to have a wider bandwidth. So again, narrow bandwidth, longer durations, wide bandwidth, shorter durations. So clearly in terms of overall time saving in a sequence, this one is going to be preferable because we only need to have the frequency encode gradient on for a relatively short time. Now, to be able to do that, of course, you need to have a sufficiently strong gradient system, or you will not be able to hit a sufficiently strong gradient to get the area required. Now, if we choose a narrower bandwidth, that will actually deliver a better image SNR, signal to noise ratio. So why is that? Well, just consider this kind of conceptual picture here where we're showing radio frequencies along here, and then we are showing which radio frequencies we need to pick up. So for a 16 kilohertz bandwidth case, we need to be able to receive everything in this range here from plus or minus 8 kilohertz around the center frequency. And again, the center frequency at 1.5T is about 64 megahertz. So essentially, we have to listen for everything in here. Now, we could plot the amplitude of the signals we're interested in on the y-axis, and we might end up with something like the yellow curve here. So this is saying there's lots of signal here at the center frequency, and then it tails off. And then obviously, once we're outside our bandwidth, there's no signal of interest at all to us. But we need to be able to pick up all the signal of interest in the echo. Okay, now if we go for a wider bandwidth, it's more or less the same picture, except this time we have a wider bandwidth. So same idea, this is the range of radio frequencies out there, and we need to be able to listen for a certain bandwidth of frequencies. And in this case, because we're listening for a wider bandwidth, we have to obviously allow in a wider range of frequencies. So our signal, our echo decomposed into a spectrum, might look something like our yellow curve here in this instance. Okay, so trying to achieve the same thing, you're trying to receive all the frequencies that are of interest in a given bandwidth setup. Okay. Now the problem is not only will there be signal there, there will also be noise there. Okay. So we're showing the noise here in this pinky color. And what this is showing is that at different radio frequencies, we can expect there to be noise components. So within our 16 kilohertz bandwidth in this case, as well as the signal that we're showing in yellow, we'll also pick up noise. In other words, data or information that's really got nothing to do with the image. And that's going to appear in your image as poor signal noise, as granularity, as noise on your picture. Now we only need to pick up this bandwidth, which means that the noise outside of those frequency ranges gets ignored, which is good. So the noise that's shown here and here will not contribute to the image. And noise is unavoidable. It's just part of natural physical processes that are going on in or around the MR scanner. Now, when we go to a wider bandwidth, what we find is not only do we need to widen our bandwidth to pick up our wider bandwidth signal, but we're also picking up a wider band of noise just by virtue of this window needing to be wider, the window of frequencies or the bandwidth that we need to pick up. So that just means that for a wider bandwidth case, we're picking up more noise than we do in a narrower bandwidth case, and that noise gets translated into worse signal to noise ratio on your image. Another effect of bandwidth is on the minimum TE value that we can use in a sequence. So it turns out that choosing a narrower bandwidth means a longer minimum TE. Okay, now that sounds a bit complicated, so let's just look at it on a spin echo sequence to see what we mean. So here we have a 9180 radio frequency transmitter for a spin echo, and here's our echo, and this is our TE value. So here we're assuming that we've set a wide bandwidth, and with a wide bandwidth we say we've got a shorter echo, so we wouldn't expect the duration of this echo to be overly long. Now, say we want to reduce the TE value from what we have shown here. Well, that's fine. We can easily do that. We just set a shorter TE value. It just means the 180 is going to move a little to the left, and as a consequence, the echo is going to move a little to the left. There's no real restriction on it. There's plenty of room there to reduce the TE and to move things around a little. Now, say we were dealing with a narrow bandwidth case, and remember, with a narrow band, we expect to get a longer duration echo, as we've shown here. Okay. Now, say we want to reduce the TE in this case. Now you can see a difficulty because the echo is already just about clashing with the 180. The start of the echo is just about clashing with the 180 degree pulse here. So we don't really have any room to reduce the TE time anymore. Okay, so if we really wanted to reduce the TE here, we'd have to move to a wider bandwidth, okay, and shorter echo. So to go back to the original statement, which sounds a little confusing, but what it's saying is if you choose a narrow bandwidth, as we have done here, it means that you are going to be stuck with a longer minimum TE. You can always increase the TE, but you are stuck with a longer minimum TE. Okay, so after all this on bandwidth, you might want to know, if you sit down at the console, how do you actually specify the bandwidth? What's the number or numbers that you put in? Well, it depends on the system. On Philips systems, the bandwidth is specified as a kind of an inverse quantity, which is called water-fat shift. So if you remember, we said that bandwidth impacts on the chemical shift artifact, the degree to which the water and the fat images get shifted. Okay, so with the Philips system, where they use this water-fat shift number, you specify that in a very direct way. You just say, I want a water-fat shift of 3 pixels or 2 pixels or whatever. And that's what you will get. But what you're really doing underneath all of that is you are setting the bandwidth. On other systems, the bandwidth is put in maybe a more physics kind of way, where we specify bandwidth in terms of hertz per pixel. So what does that mean, or how does that look? So say on one of these systems we have a setup like this, and from what we've seen before, we're going to have a certain bandwidth across our image. In this case, we've got a bandwidth of 32 kilohertz. Just as an example, we've a bandwidth of 32 kilohertz across our entire image. Okay, and we've set our image up to have 256 pixels in the frequency encoding direction. That means that the 32 kilohertz is going to be distributed 256 pixels. So the difference as you move from pixel to pixel in Larmor frequency is going to be 125 hertz per pixel. And that's the number you would type in. You would type in, I want a bandwidth of 125 hertz per pixel, as here, or 150, or whatever it is you want to set. So that's the way on a Siemens system or on other systems that you may specify the bandwidth. Okay, so we introduced chemical shift at the start, but we're not in a position to explain why it happens and why bandwidth has an effect on it. So the essential reason behind it is that fat and water process at slightly different frequencies. So in a 1.5T system, fat processes about 220 hertz more slowly than water. So it's a very tiny difference, given that water is processing at a procession frequency of about 64 megahertz, but it is a difference. So using our way of setting up bandwidth now that we just covered, say we set up as an example that we have a bandwidth of 62.5 hertz per pixel. Okay. So let's imagine we have a slice, maybe a transverse slice through an object or through tissue. And to make things a little easier to understand, we're going to separate out the water part of that image and the fat part of that image. Now, obviously, in the real world, they're both mixed in together, but for the purposes of illustration, we're going to consider them as separate for the moment. So what's happening? Well, during readout, any given column in water and any given column in fat is going to be processing at a certain frequency, a certain Larmor frequency, given its location in the readout gradient. Okay. Now, because we've set up a bandwidth of 62.5 hertz, we know that as we move from column to column, the difference in Larimer frequency is going to be 62.5 Hertz. So if we move from this column to this column, the Larimer frequency goes up by 62.5 Hertz. If we move from this column to the next one, it goes up by 62.5 Hertz, etc. Okay? And it's the same for fat. This column is going 62.5 Hertz faster than this column, etc., etc. Okay, so say we choose some particular column in the water image. It doesn't matter, any one of them. Okay, so we pick a column. Where are we going to find in the fat image a column with the same precessional frequency? Okay, well, you might think, okay, well, it's just be directly in the same location. Why wouldn't it? Well, it won't be because of this 220 Hertz difference between fat and water. Okay, so if we are looking for a fat column that has the same Larimer frequency as a column in the water image, we're going to need to move a number of pixels to the right into the stronger frequency encoding gradient to make up for that 220 Hertz difference in fat and water. Okay, so if we pick any given column, in this instance, because we have a bandwidth of 62.5 Hertz, to make up that 220 Hertz difference, we need to move 3.6 pixels to the right, assuming the right is moving into the stronger frequency encode gradient, to find a column in fat that has the same precessional or Larimer frequency. Okay, so if you just do the sums, you'll see that the bandwidth of 62.5 and the pixel shift of 3.6, it corresponds, I think, a little bit more exactly to 224 Hertz, which is probably a little bit more accurate than the 220. Okay, so why is this causing the chemical shift artifact where we see this slippage between the fat and the water images? Well, remember, position in the frequency encoding direction, which we're taking left-right here, position and frequency encoding direction is encoded by the frequency that the MR receiver hears, effectively. Okay, so it doesn't see any of this. Remember, all it's going to hear is radio frequency signals that are picked up on the radio frequency coil, and it will have decided that a certain frequency is associated with a certain column, and it will allocate the gray levels on your final image according to that thinking, if you like. Now, that means that it thinks that water signals, say, that are coming from this column, and fat signals that are coming from this column are coming from the same location, which of course they aren't, but it doesn't know that. So in the final image, those two images, the water image and the fat image, are going to be misaligned by 3.6 pixels in this case. In other words, there will be a chemical shift artifact between them. Okay, so say we want to reduce the chemical shift artifact. Well, what we do in that case is we can move to a wider bandwidth. So the same process is going to happen as described already, except this time we've got a higher bandwidth. So say we've moved to, as here, a 125 Hertz per pixel bandwidth instead of 62.5 that we were using previously. So we're still going to get misalignment between fat and water in the final image, but it will not be as pronounced. That's because we are using a stronger bandwidth. It means as we move from column to column, the difference in frequencies, in Larimer frequencies, is bigger than it was. And that really means that 220 Hertz difference that we see between fat and water, it becomes less significant. Now we only have to move 1.78 pixels to find a fat column that has the same precessional frequency as a given water column, which, if you remember in the previous slide, that the at the narrower bandwidth, we had to move 3.6 pixels. Okay, so by moving to a wider bandwidth, we've reduced our chemical shift artifact, or the appearance of the chemical shift artifact. Okay, so let's summarize the important things from all of that. So like many parameters in MRI, if you change bandwidth, it does both good things and bad things. So if we increase bandwidth, what it means is we will worsen SNR, because essentially we let more noise in, if you want to look at it like that. We reduce the minimum TE that we can use, because essentially the echoes are going to be shorter and they take up less room. And also by increasing bandwidth, we reduce the chemical shift artifact. And obviously, if we decrease bandwidth, we just reverse all of those effects. Okay, so thank you very much. I hope this was useful. You'll find more on MRI Notes, and additional videos will be gradually added over the next few months.